Hi there and welcome to Workshop 8 for 161324 data mining. So today we're going to be looking at the regression classifiers, so those that are based on the generalized linear model. So we've got logistic regression, where your outcome variable is binary. And so we can't obviously use linear regression in that case because linear regression, the values of the linear predictor can take any number on the real line, whereas of course our outcome variable would just be 0 and 1. So generally what we do is we have a link function that essentially maps the linear predictor, which goes from, it takes any value on the real line and maps it to a probability. So between 0 and 1, and the idea then is that the closer your probability is to 0, the closer you are to the first class, and the closer your probability is to 1, the closer you are to the second class. And then multinomial regression is when the outcome variable is categorical with more than 2 levels. And essentially it works by doing multiple logistics. So you do a logistic between class 1 and class 2, class 1 and the other classes, and then a logistic between class 2 and the other classes, and so on and so forth, and sort of combine them up and fit it all at once. So we're going to start with an example of a logistic regression on horse colic data. So colic is a disease obviously that horses can get, and generally, or it has a fairly high death rate in horses. And we've got physiological data on a bunch of horses. So we've got a bunch of different measures on those horses, and we have whether or not the horse had colic. And we also have things like whether surgery was required, and of course some of the horses died and some survived. So our goal is to classify the horses as to whether they're likely to survive or die based on the physiological parameters. The idea being that if we can establish a relationship between those physiological parameters and the likelihood of survival, then we can perhaps make decisions about the horse prior to surgery. So we're going to start by loading a bunch of packages. So we're going to be looking at obviously the tidyverse. We've got rsample for doing our splitting. We've got skimr for taking a look at the data. We've got discrim for doing discrimination. In fact, I don't think we're going to be using that one today. I think we'll be using parsnip only. But at any rate, discrim will load the parsnip package for us. We've got yardstick for measuring performance. We've got recipes in order to do some scaling, which is going to be important for multinomial regression later. And then we're going to override the step function with stat step. And the reason is that when we load those packages in, if we have a look down here, you can see that the following object is masked from package stat. So when we load in the recipes, then we get the step function essentially overrides the existing step function. And later on, we're going to be wanting to use stepwise regression, and therefore we're wanting to run step on on either the logistic regression or the multinomial regression. And it's going to get confused because step is actually going to be taken from the recipes package instead of the stats package. So this just overrides it, and so that when we run step, we get the stats version of step rather than the recipes version of step. Okay. So whenever you load packages in, it pays to just look at the output that it's given. So for example, this one here is important. We're going to be utilizing this we utilize this in lecture 8 and lecture 9, and that is for binary classification, the first factor level is assumed to be the event. This is actually the opposite of what you'd normally do. Normally we'd consider the second factor level to be the event. So for example, if you're fitting a logistic regression, then your outcome variable is usually the second factor. So if your probability turns out to be close to 1, then you usually favour the second factor rather than the first. So the event is usually the second. So typically we will be using event level equals second in our modelling. In our metrics for evaluating how well the models do. Okay, so that's why we're overriding step. Another really common one is select from the mass package. So if you load the mass package, MASS, all in capitals, then that will have a select command in it, And of course, dplyr has a select command in it. And you'll find that whenever you want to use select, you'll almost always want to use the dplyr version, not the mass version. So that's one thing to watch, is if you load the tidyverse before you load the mass package. So for example, LDA is in the mass package along with a whole bunch of other modeling tools. Then if you do that, then whenever you run select, you'll get the mass version of select, which is not what you want, and you'll get very strange error messages. So there's just something to watch. Whenever you loading a whole heap of packages, just watch the messages that get pumped out of them, and just assess whenever you have an object masked, that's basically meaning that function will be overridden by the last package that you load. Okay, it's just something to watch. Okay, so we're going to run the whole block, which is going to read in our data. Let's have a look at it. So we've got 368 rows. We've got whether they had surgery or not. We've got a bunch of physiological parameters. So we've got their rectal temperature, we've got their pulse, respiratory rate, and a bunch of other things here. And somewhere over here we've got died. Okay, and so our outcome variable is going to be whether they died or not. And then our input variables will be all of the other ones. So our predictive variables will be all of the other ones. Okay, and we've split it into a training set and a test set in order to train our models up on the training set and then assess the performance on an independent subset. Notice that we've also mutated across a bunch of variables and turned them into factors, because by default read underscore CSV is going to read everything, read all the factor variables as being categorical, so just character strings, and so we want to convert them to factors so that our modelling tools later on know that they're a factor directly. In particular, for doing our so it's particularly important if the outcome variable is not binary. So if it's binary, then it's okay because it's 0, 1, that's fine. But if it's not 0, 1, like our data is, so you can see our outcome variable is just 0, 1, our died column. If it's not, and it's like, for example, we were modeling young and old, that was our outcome variable, then it's very important that it's converted to a factor variable, because if it's not converted to a factor variable, then the modeling tools will break. So the modeling tools are expecting the outcome variable to be a factor. Okay, so we're going to start by using logistic regression with the GLM engine to build a logistic model for the died based on all of the other variables. So we're going to start with a logistic regression specification. Our mode is going to be classification and our engine is going to be GLM. And then we might as well fit straight away. We're going to fit our died variable in terms of all others using our horse training data, and we're going to store that into let's call this one. I think we're going to probably do more than one. So that's had a fit, and we could have a look at this model. So you remember that the outcome type here, because we fit it within the tidy models framework, it's going to be a parsnip model object. So things like summary won't run directly on this. Okay, but you can nonetheless see that we've clearly fitted a model. Okay, we've got the coefficients for the model here. We've got the degrees of freedom and the deviance. You remember the deviance is essentially the equivalent of the residual sum of squares. Okay, so we want to get a perhaps the summary table for the GLM, and so we could do this by extracting the fit engine. So you remember, extract fit engine just gives you the underlying model object, so it's going to be give us directly the object that's returned from GLM. Okay, so now you see we've got the same output, but we don't have the parsnip model bit because we've extracted the fit, and then we could run summary. Okay, so there's the summary table, which is very similar to the summary table that you would get from a linear regression, right? In that you've got the intercept term, and then you've got each of the effects here. And these effects are for the linear predictor, so these are on the logit scale. So you remember that there's a transformation between the linear predictor and the outcome variable, the response scale, which is a logistic function. So we've got the log odds, which is log of p over 1 minus p, is modeled on this scale here. So if we want to interpret these, basically if they're bigger than 0, so if they're positive, then it's a risk factor for the outcome variable. So the outcome variable is died. So when died is 1, obviously the horse died, and when died is 0, they survived. So positive numbers are associated with death, and negative numbers are associated with survival. Obviously, we've got to take into account our standard error. So we're going to only be looking at the terms that have positive association. So you can see here that there is some association with pain. So the animals that had the higher pain scores tended to be more associated with death. So those are the animals that are more likely to die, obviously, compared to those that had low pain scores. We can also see that there's a positive association with packed cell volume, in that the larger the packed cell volume is, the more like death, and of course there's an association with age, so older horses were more likely to die than younger horses. Notice that there is an association with surgery, but it is not significant, in that if the horses had surgery, they were more likely to die, but there's quite a bit of uncertainty associated with that measure. Okay, and of course this shouldn't necessarily be surprising, because presumably there'll be some selection for surgery. So some of the horses, if their colic was particularly bad, perhaps those are the ones that are selected for surgery. And so the fact that they died is just it may be an underlying measure of the severity of the disease, rather than as a consequence of surgery. Okay, so this is suggesting that the horse doesn't have surgery, they're more likely to survive, but that may just be the underlying severity of disease. Now we could have also got this using the tidyverse. So one of the nice things about Parsnip is it implements a wrapper around Broom. So tidy will operate directly, and you remember tidy from Broom gives us a data frame version of the summary table, so the coefficients. So we can grab a summary of the summary table directly from the model using tidy, and I think glance might work as well. Let's test it out, see whether it does. Yeah, so glance also works. So basically, it just basically runs extract model fit and then runs glance on it. And so you can pull out the AIC. So you remember that's the information criterion, and you can pull out the deviance and the null deviance. So the null deviance is essentially the sum of squares before fitting the model, or sum of squares after fitting an intercept only model, and the deviance here then is reduced, obviously, after we fit our model. So it's basically telling us that something in our model is important, which isn't particularly surprising. Okay, now let's have a look at the odds ratios. Now you remember that an odds ratio, so you remember that so let's write a little bit about this. A logistic regression takes the form, so we're going to write some maths in LaTeX. It'll come out nicely on the HTML, you don't have to know how to do this. So what we're going to do is we're going to say yi is going to be Bernoulli. So we're going to sim, aren't I? So let's write it in a serif font. Again, you don't have to know how to do any of this. This is just how maths is written. So this is the LaTeX or MathJax language. And so we've got some probability of being a case. So probability of death is what pi is. The yi is 0 or 1. That's 0 if it's survives and 1 if it's death, and pi is the probability of death. So this is like a binomial, but you've only got one trial. So it's like tossing a coin, where the weight of the coin is pi. So the probability of heads is pi. And then our pi going to put it in an aligned environment. Our log is going to be our linear predictor. And we may have P predictors. Okay, so we get some system like this. Okay, and logit here is just log of pi on 1 minus pi. Let's make those brackets look a bit tidier. Okay, so there's our maths there. Okay, so we've got our linear predictor here, which then gets exponentiated to give our odds ratio. So the odds ratio, you remember, is the probability divided, is the ratio of the probability of success to the probability of failure. So that's the probability of the event happening to the probability of the event not happening. So for example, if you've got a probability of something happening that is say a third, so the probability of, well, let's use 0.2. Okay, so if the probability of success is 0.2, then the probability of failure is 0.8, and so your ratio there is 0.2 divided by 0.8, which is a quarter. So your odds are 1 to 4, which makes sense, right? If your probability of something happening is 0.2, then there's one chance compared to 4 chances of it not happening. Okay, so that's how odds work, and so the log odds is what's given by the predictor, and so the odds ratio is the ratio of pi over 1 minus pi for a predictor variable there compared to not there. Okay, so to work it out, all you have to do is you exponentiate the associated coefficient. Okay, so to answer this one, to get the odds ratio, we just have to exponentiate the coefficients. So what we would do is we would grab our tidied data, right, which will give us our estimate, and then we would compute a new column for the odds ratio, which is just going to be the exponentiation of the estimate. So you can see here we've got our odds ratio column here, and then we're just going to filter for our term is equal to surgery 1. So this is whether they had surgery or not. Okay, so we can see the odds ratio is 1.4. .447 or 48, I guess. So there is an increased risk of dying following surgery. Okay, so essentially the odds ratio is the multiplicative factor of the of dying versus not. Okay, so if you're comparing two horses that are the same except for the surgery variable, so they have the same underlying physiological parameters, but one had surgery and one didn't, the difference in the linear predictor is given by the coefficient of surgery, right? Because one of them has surgery set to 0, so the coefficient is not included in the linear predictor. The other has the coefficient 1, so the coefficient is included in the linear predictor. All other things are the same, so the difference between the linear predictors is just given by the coefficient. In this case, maybe it's beta 1 is the coefficient of surgery. So if you take the ratio of those two things, because this is on a log scale, when we take the ratio, it's equivalent to taking the difference, and therefore the log of the ratio, the log of the odds ratio, is going to be just equal to the to the coefficient. So the odds ratio is just going to be the exponentiation of the coefficient, which is what we've done here. Okay, so we'll write, this isn't really surprising, as surgery is likely reserved for the horses with more severe disease, i.e. they may be dying as a result of the more severe disease, not as a result of surgery. In addition, the p-value here is high, so we have lots of uncertainty about this. Okay, so now we're going to perform a prediction on the test data. So we're going to take our horse LR1 and we're going to augment the test data. Right, and so we get our outcome variable over here. We get the predicted class, and then we get the probability. So you can see that for this first class, we've got a 96% chance that it's that the class is 0, and a 4% chance that it's class 1, and of course that was correct. Whereas for this one here, row 3, we have an 84%. So the model thinks we've got an 84% chance of death. So that's what it's been allocated to, but in fact it didn't die. So we could then, so these are our predictions. Okay, and we could then assess the confusion matrix. So the truth is going to be the death column, died column, and the estimate is going to be our prediction in the class. And you can see that we get 70 correct and 22 wrong. So our accuracy is 70 out of 92, and we could work that out directly as well, of course, using the accuracy function. Okay, 0.76, so misclassification rate is 0.24, 24%. Okay, so now we could see that when we looked at this if we looked at the table here, summary table, lots of these p-values are large, right? So a lot of these variables are having to be estimated but don't seem to be telling us much about the outcome variable. Perhaps they might be correlated or something like that, so we may want to reduce the number of predictors that we put into the model, and we can do that with step, but remember that our model outcome, so if we look at our horse.lr1, it's a parsnip model object. It's not a GLM object. So if we run step on that, it won't know what to do. Okay. And even if we run step on it after extracting the model fit, oh, it does work. Oh, no, it doesn't. There we go. So it starts running, but then it dies because it doesn't actually have the underlying data anymore. And that's just a consequence of how Parsnip is wrapping that model object. It hasn't actually embedded the data. So usually when you fit a GLM, it actually embeds the data in the model object. And in this case, we haven't embedded the data in the model object. And that's basically because Parsnip can do other things to the data first. So for example, if you use the workflows package, then essentially that can do the wrapping of things like your transformation of variables or any of the normalization steps. So your recipes on your data, it can sort of build those in to the modeling process. And so the data that's actually used to fit the model might not actually be available to be stored in it necessarily. So instead what we've got to do is, if we want to run stepwise regression, we've actually got to refit the model completely outside of the tidy models framework. So let's just make a comment. This won't work. Reason is that Parsnip uses a slightly different storage method. So the underlying GLM object doesn't have the data at hand to be able to refit the data frame, refit the model over and over. So I'll just add val equals false just so that it doesn't get evaluated when we run the when we knit it later on. So instead we need to refit the model directly in GLM. Okay, so we're going to refit the model. It's just going to be GLM died in terms of everything. Our family is going to be binomial, and our data is going to be our horse data. Right, so we're going to get the same output here. Okay, exactly the same output as we had before. Okay, but now of course we can run step on it. Okay, so you can see that it runs and drops quite a few variables out. Okay, so you come down to quite a small model. So let's save that output. Okay, and then we could have a look at so we could summarize that model. And you could use the tidyverse for this. You could use broom tidy for this instead of summary. So let's have a quick look. Okay, so you can see it's a much smaller model. The residual deviance is 233, whereas before it was, good question, what was it? The residual deviance was 216, so this isn't as good a model fit, but of course that makes sense. We haven't used as many variables. Okay, so it's the bias variance trade-off, right? So to evaluate model performance, we could do it all in base R, but it's much easier just to switch it to okay, so we could do it in base R, so we could do this manually. So for example, we could take our model fit and we could use augment with the horse test data. Let's have a look. New data. All right, so that's going to give us a new column, and this here, this new column, is the linear predictor. So we could instead do, is it type.predict? We could switch to the response scale, and so there's our predicted probabilities. So we could do this manually by computing, by using augment to produce response variable predictions. Predicted probability of died equals 1. Then classify using p-died greater than 0.5. Right, so we could augment it, then we could mutate and introduce a new variable, which is going to be our predicted class. Is going to be, so what it's going to be, well, we're going to have to switch based on what type of variable that is, right? So we want a factor variable. Equal to if it's greater than 0.5, then it's going to be 1, and if it's less than 0.5, it should be 0. Okay, so now we've got our predicted class here. Okay, and then we could, so that's going to be our prediction from the second model, and then we could just do our usual confusion matrix where our truth is died and our estimate is our predicted class. Okay, so you can see here that we're doing basically, we got exactly the same, right? We got 22 out of 92. Alternatively, and much simply, we could refit in the tidy models framework. Right, so the problem with doing it this way is that for a start, the code is more complicated. You've got to remember to switch your predictions to the response scale and to compute your factor, and the factor has to be around the right way. So we have to remember to get the labels here around the right way for that factor variable. We have to convert it to a factor in order for confusion matrix to work, and so on and so forth. But the alternative is just to refit it in the original framework. So if we grab a logistic regression and we fit using the same variables, right? So if we have a look at our model fit, we had rest rate. We got died in terms of rest rate, in terms of temp extra. In fact, we could get it just from here, even simpler. Data equals horse.train. Okay, and so this is going to be our, and then we could just do our usual augment and compute the confusion matrix directly. And of course, augment has computed the correct class in this case now. It has done all of that transformation for us. And we will, of course, get the exact same table. So the misclassification rate is the same as the big model, but we have a much simpler model now. Okay. So that's logistic regression. Next, we're going to use multinomial regression with an example from the notes. So if you're looking at the study guide, this wine data will be familiar to you. And in fact, I think we fit this wine data using a multinomial regression in the notes as well. It's just this time we're going to be using we're going to be scaling. So a multinomial regression is fit using the MNet package. So it's actually fit using a package designed for neural networks. And the reason is that there's that logistic regression and multinomial regression are actually really similar to a neural network, because you remember a neural network takes a linear combination of the predictors and then does a sigmoid transformation or a logistic transformation, logit transform on them, in order to get a probability scale for the hidden units. And similarly, if you're doing classification, you do the same thing. You take a linear combination of the hidden units and do another sigmoid transformation at the end for the outcome probabilities. So a logistic regression is the same as a neural net where you just don't have a hidden layer. So there's no hidden layer, so you're just taking a linear combination of the input variables, and you're then taking a sigmoid transformation at the end. That's exactly the same as what we're doing in a logistic regression. So when we go to doing multinomial regression, we fit it in exactly the same way as we would fit a neural network. And as a consequence of that, we've got to be careful, just like we do when we have to fit a neural network, that the scale of our predictors are relatively small. And the reason for that is that you remember when you fit a neural network, what you do is you randomize the weights, which are the coefficients of each of the variables. And if some of your variables are large, then when you multiply it by that random coefficient, you get a very large number for the linear predictor. And if you've got a very large number for the linear predictor, and you then transform that using a sigmoid, then you either get 1 or 0. Right? So if it's a very large positive number, you exponentiate it, you get essentially infinity, you run out of space in the computer to store that number, and therefore you basically get 1 or 0. And therefore moving that weight doesn't really make much difference to the 1 or 0. You don't actually move the outcome variable at all, or the probability that you're working out on the hidden node. Therefore you can't improve it at all, because essentially it's reached convergence already, even though of course it's miles away from the actual optimal model. So that's why we transform things for a neural network, and because the multinomial regression is going to be fit with the same code that fits a neural network, we've got to do the same thing. Okay, so this data on wine, basically we have 3 cultivars. So let's have a look at it. We've got 3 cultivars, A, B, and C. And then we've got a bunch of numeric predictors on the content thereof. So we've got alcohol content, we've got malic ash content, magnesium content, various phenols, and so on and so forth. We've got a color level, some hue information, and other things. You can read all about these things in the notes if you're interested. So the goal, of course, is picking the cultivar based on these chemical characteristics or biochemical characteristics. Okay. Right, so we're going to do this with multinomial regression. And so multinomial regression. Okay, so the mode is classification, and the neural net is nnet is the engine, so that's fine. And then we're going to run fit, and we're going to fit the cultivar in terms of everything else. Now let's set the random seed, because you remember that the neural network by default will be setting random weights, and we want those weights to be the same. So I've run the fit, and so now I'm going to assess whether this thing actually converged. So we can have a look at the model output. So these are the coefficients. We'll talk about those in a moment. But to see whether it converged, what I want to do is I want to pull out the extract the fit engine, and then I want to look at the convergence object from that. Okay, it has actually converged. So the convergence object, the convergence value from the underlying model fit is going to be 0 if it's achieved convergence, and if it hasn't achieved convergence, it's going to be 1. Okay, the other way you can do this is, instead of extract fit engine, you can just pluck fit and then convergence. Okay, and the reason is that the wine.mn1 object underneath that object is just a list. Okay, and one of the entries in that list is fit. And all that extract fit engine is doing is it's just pulling out that fit object. And so we can actually get that same object by using pluck. So pluck is just the tidyverse way of pulling something out of a list. And so you can see here that if I just pluck the fit object, then I get the mnet multinom object. So when I then pluck the convergence entry out of that, I get a 0. So this form here with the comma is just a simple form of doing this. So first pluck the fit object and then pluck the convergence object out of that. Okay, so it's just a way of dealing with lists, lists of lists, so recursive lists in R. It's much more powerful, the pluck command, than what we're using here. So we've converged, hooray. Right, so now we can then, perhaps we'll take a look at it. So let's just say, okay, so we could take a look at the model. So we could have a look at, I'm not sure if tidy works on this. Let's have a look. No. It doesn't work on all model types. So we could extract out for the engine. Okay, so you can see here that it's got coefficients for class B and coefficients for class C, but it doesn't have any coefficients for class A. And the reason is, of course, that if you know the probability of class B and you know the probability of class C for any of the observations, then you also know the probability of class A, because it can only be one of class A, B, or C, and those three probabilities, of course, are mutually exclusive, so have to add up to 1. Okay, so you only need the probability of class B and C in order to infer what the probability of class A is. So these are the coefficients of the linear predictors for class B and C. Okay, and there will again be a logit transformation to get that back to the probability scale. So let's now see how well we do on the test set. So we'll take our wine.mn1 and we will augment it with the test set. Right, so that of course will give us the probability. Let's have a look at it in here. So that of course give us our predicted class and then each of the other things. And you can see that the predicted class is class A with almost 100% probability here. Or it's class B with almost 100% probability. So we're super certain here about the classes in each case. And that gives me pause, because you shouldn't expect a prediction of 100% across the board for every class, for every observation, right? A model shouldn't be this certain about the outcome variable. Essentially what's happened here is that we're almost perfectly dividing the outcome. And this tells me that perhaps the values of the linear predictor must be very, very high, very, very large in magnitude, right? In order to get a probability of 1, right, after a sigmoid transformation, the value of the linear predictor must be very, very large, either positive or negative. And that tells me that perhaps I've got to be cautious about the scale here. And in particular, we see that proline is very large in magnitude. Some of the other ones are large in magnitude, but not too bad. So magnesium is also very large in magnitude. And so I wonder here whether we've got the situation of starting out with some random weights, and those random weights essentially, the random weight for proline is maybe like 0.5 or something, and so we've got e to the 500 essentially, exponentiation of 500, so we're running out of precision in the computer, and therefore our probability of each class is 0 or 1 on the training set, and therefore we've converged, or we think we've converged, even though we actually haven't moved at all, and we've just got some random starting position that does not reflect the data at all. And this probably, we could sort of confirm this by having a look at the first rows of the test set. So all 10 first rows are predicted to be class A. What are they? Oh, they are actually class A. So maybe this is actually okay. Let's have a look by having a look at the confusion matrix. Okay, and actually it's not too bad. We are actually predicting it 100%. So it might be that the reason that the probabilities are so high and so close to 1 here is that actually this data is just really, really easy to separate. But we can see that we got it wrong in 4 cases. And you remember that when we got it wrong, well, let's have a look. Let's have a look at those cases in detail. The predicted probabilities all looked really close to 1 and 0 for each class. My initial feeling was that we may be having computational problems in that the initial weights caused the linear predictors to be large in magnitude, so that we ran out of in the computer and thus converged to a very unoptimal endpoint. But the predictions seem okay. We only get it wrong 4 times. Let's see what the predicted probabilities were for the ones we got wrong. Right, so what we can do is we can just filter the data for where the cultivar and the predicted class differ. Okay, so we can see that 3 of them are B, the first 3 are B and the last one is C. And then we could just look at the predicted probabilities, and you can see that they've all been predicted as class A and all with very high confidence. So the model is very certain that these 4 observations should be class A, but in fact they're not class A at all, they're class B and C. So I'm starting to go back to maybe we've reached a optimal value for the linear predictor that is actually, it's doing well, but it's not actually converging to the optimal sort of model fit. Hard to tell exactly what's going on here. But one way to do it, of course, is scale the predictors, right? So we know the predictors are on a very large scale, so we should scale them anyway. So let's create a recipe to scale our predictors. So our wine recipe is going to be a recipe, and it's going to be a recipe for the cultivar in terms of all other predictors. So you remember that the specification here, the recipe here, the functional form here, and the data set is just to get the roles, right? So we've got one outcome variable and one predictor. Okay, and then we're going to step normalize all our numeric predictors. Okay, so now when we look at wine, we've got centering and scaling for all the numeric predictors, and then we're going to prep that on the training data. So our wine.res is now, so create a recipe, normalize all the numeric predictors and prep it, train it using the training data. Right. And then now use this to fit the multinomial model. So what we're going to do is we're going to bake our training and so we're going to bake our training data now, and we're going to bake our test data. Now you see here that I've said new data is null, and so that's so if I bake a recipe and I don't supply any new data, then it will use the data it's been trained with. Okay, so this is equivalent to running new data equals wine.train, except when you do that, it recomputes the so it uses the centers and scales that it's computed in the prep stage. So you remember the prep stage here doesn't actually scale the data. All it does is it works out the transformation required to scale the data. So it trains the transformation. If when you bake a recipe, if you give it no new data, so you apply new data equals null, it will just give us the training data back, or the data that you prepped it on. So if you have a look at wine.train.bake, you can see that that is in fact the scaled data. So I've got my cultivar and I've got my scaled data, and then of course if I want to bake the test data, I've got to supply it so that it can apply that same transformation. Okay, now it's not a huge, so I could have also done new data equals wine.train here, and it would give me the exact same answer, because of course the data that I've baked on is the data that I've prepped on is the same data that I've baked on. But you can set up recipes such that some steps are skipped when you supply new data, and so we'll see that, and I think it's lecture 9 next week. We'll do some oversampling in order to deal with some class imbalance, and that's something that you don't want to do in the test data. So oversampling basically essentially replicates data so that your classes are the same size. And you don't want to do that to the test data because, of course, you're essentially creating artificial data. And if you create artificial data and evaluate performance on artificial data, that's not actually performance on the real data at all. But it's okay to train on some artificial data if your purpose of training on the artificial data is to correct some class imbalance. So that's why I've introduced that here. Okay, so now that we've baked the data, we can refit the model on the baked data. So we'll have a second model fit, which is going to be our multinomial regression. We're going to fit our cultivar in terms of all our other data using our baked data. Right, and then we're going to use prediction on this. It's going to be wine.mn2 augment. Now I should probably first test convergence. Yep, it's converged. And then I can augment it, and now perhaps we could have a look at this. Oh, I'll do this. down here. So let's have a look at our model fit. So again, we do actually have very strong probabilities. So the scaling may not have been the underlying thing, although they're not perfect. So here we go here. Here's one where we're not so certain. So we've got an 81% chance of class A and an 18% chance of class B. So it's not that clear separation that we had before. Well, it's clear separation in many cases, but not clear separation in all cases. So here's another one where we've got a 15% probability of class C and a 85% probability of class B. Right, let's check the model performance. So let's take our predictions and we'll compute the confusion matrix. Okay, and you can see that we're doing much better. Again, we're getting 2 in class B wrong, but the class C ones are okay. And we could also look at where we're wrong. So we're going to filter out where the cultivar is not equal to our predicted class. Okay, and if we look at our probabilities here, then actually we're fairly certain by the looks of these. So it's interesting, the ones that we're getting right that we weren't getting right before are possibly ones that we were less certain about, but these ones were actually pretty certain that that this one is class C and that this one is class A. Okay, so we're still getting those wrong fairly certainly. Okay, and the last thing we might want to do is, we've used all variables, but we're also getting very, very high quality predictions, so we may be able to get away with fewer variables, and so we could run step again. In order to run step to simplify them, we need to do that outside the tidy models framework. Right, so we've got to take our model 2 and we'll refit it using Multinom from the nnet package. It might run directly, let's have a look. So cultivar in terms of everything, and we're going to use our baked training data. Can't find function multinom, that's because we haven't actually loaded the nnet library. So let's load that now. Okay, we should really be setting the random seed here, shouldn't we? Nonetheless, it's converged, so that's okay. So we could run step on, this is a model refit, isn't it? Let's call that model refit, because I've just overwritten that original data. So this is the refit, what we're going to do for model 3. So we're going to run step on that. Okay, notice that it actually hasn't converged at that last one, so it stopped after 100 observations for some of them. So we're going to redo this. I'm not sure if we can apply this to step. Let's have a look. So what we want is we want to go step. We want to look at the help for step multinom. What's that class? Let's have a look. Maybe we need to do step innet. Interesting. So innet, so step has a, so I think that, so right, so let's have a look. Let's see if we can figure out what's going on here. So what does step actually do? Step actually uses add one and drop one repeatedly, and it will work for any method for which they work. So what's actually being done here is add one, well, drop one, multinom. Let's have a look at the help for that. Okay. So I'm seeing whether we can pass in parameters that go to the underlying fitting function. Yes, additional arguments for innet. So what we can do is we can actually, we should be able to pass in max iterations, and it should work. Let's see. So I'm going to set the seed here. It's still converging under 100 iterations. Is the innet, is the max the correct thing to be passing in? Let's look up the help for innet. I think it is, isn't it? Yeah. So for some reason it's not been passed through. I'm not quite sure why that would be. It may be that it's not passed through via step. Let's have a look here. Dot, dot, dot. Any additional arguments to extract AIC. That's not what we want. We want any additional arguments to drop one or add one. So I'm not sure if we can actually drop them through. So what's happening here is that the step function is repeatedly calling add one and drop one on the object, which is calling through to add one and drop one in the innet library on the multinomial object, but it's not actually passing the additional parameters that we pass into the step function through to add one or drop one. Instead it's passing them to extract AIC, which is not useful to us. So I'm not quite sure how to define this. Let's have a look at the help for innet again and see whether we can set the default for max IT. I don't think we can. We may be able to set it as an option or something so that it always uses a certain value. No, I'm just going to have a quick look at the code for that. So it's there, it doesn't actually tell us. Let's have a look and see whether. Yeah, no, it's not actually. It's calling innet.default. I wonder if that has, if there's another way that we can set the number of iterations. Let's have a look. So here's the code for innet.default. Max iteration. See, it defaults to 100. Does it actually do something if that is missing? Just seeing whether it actually uses. No. So this is creating the network here. Yeah, it's putting the max iterations directly in here. So this is underlying C code for the neural net. So it doesn't look as though we can specify that outside, which is a bit of a bummer. Anyway, I shall do some Googling on that and see whether there's a way to do it later on. In the meantime, we'll accept the answer that it's given. So I'll just write a note. There doesn't seem to be a way to pass max iterations down through step. So we'll have to deal with the convergence it results in. Okay, so what does our model look like? Let's have a look. Okay, so here it is here, the final model. We end up with just 3 variables, malloc, proline, and flav. So we could try refitting with those. We can just copy the formula. So we can refit with the tidy models framework, and then we can augment with our baked training data, and then we can do our we could check our convergence, of course. We need to reset the seed, don't we? So this is reproducible. Let's have a look at our convergence. Our convergence is 1. So we haven't converged, so let's add some epochs. By default, that's not actually a parameter to multinomial regression. No, so we're going to have to set that in the engine. Max it. Still hasn't converged. Okay, let's just check that we've actually try even more iterations. Still hasn't converged. It doesn't seem right. It seems as though we're not actually passing this through, are we? Oh, no, it has. A huge number of iterations to converge. That's interesting. Okay, and let's have a look then at our fit. So there's our predictions. We can compute the class, and we can see that we don't do terribly well, actually, do we? And I wonder whether we're overfitting here, because we had a huge number of iterations required, which often in a neural net suggests that you're exploring a something with a really small residual deviance. I wonder if we change the random seed, whether this will change things. Let's have a look. Yeah, you see your residual deviance here is quite different, and our overall model fit's about the same. Okay, so we are sort of still still tending to the same spot, and we're getting not a very good prediction. So that's interesting. I guess we could see, just for interest's sake, where we're getting things wrong. And we could select our cultivar and all our predictions. Yeah, so you can see that we're actually really so we're super confident about these wrong predictions, which is interesting. So with those 3 variables, we're not actually doing terribly well with our neural net. So even though it's fit the training data really well, it maybe as overfit the training data, and this doesn't seem to be all that dependent on the random seed. I've done it 3 different random seeds and it's got the same answer each time. So that's interesting. So the fit here is much worse. We're getting 11 wrong, whereas before we only got 4 or 2 wrong. The model is also taking a long time to converge. I did use the baked data, didn't I? Yes. Which might suggest it's overfitting. But this doesn't seem to be dependent on the random seed we start with, which suggests it's finding either different local minima or the same global minima that is nonetheless overfitting. I guess we could test for overfitting by just fitting on the training data, by augmenting the training data. And computing the confusion matrix of that, or just to see whether we are actually overfitting. So what we'd expect is that the confusion matrix would look, yeah, so we are. So we're perfectly fitting the training data, is the problem. And so because we're perfectly fitting the training data, we're not generalizing well to the independent test set. And so that's a problem with a super flexible model being applied to a very small data set. Okay, so that sort of makes sense. So okay, so right, I'll just knit that and we'll finish.